Okay, so we're still busy with similarity. However, all the examples we did yesterday, pretty much what they did was they told you which two triangles needed to be proven similar. So they said, prove triangle ABC similar to triangle PQR. So you knew what the two triangles were, and not only did you know what the two triangles were, you also knew what the corresponding angles were. So those were actually pretty easy. We considered those ones higher level 2s or easy level 3s. They weren't really horribly difficult because you had lots and lots and lots of clues to work from. Do you understand? However, the more complicated ones, which will be considered higher level 3 questions or even easy level 4 questions, are ones where the triangles are not stated. They don't tell you what the two triangles are. What they ask you is they ask you to prove a proportionality statement. So the proportionality statement normally says AB over CD is equal to KL over M, you understand? Or, careful, they could go and they could ask you the multiplication one, meaning PQ times QR is equal to AB times BC. But the moment you see that relationship between sides, either proportionality or multiples of sides, you know it's a similarity or it could be your proportional division theorem. Okay, but after we've done today's ones, I've managed to get pretty much every single similarity and proportional division theorem question in the last, must be the last like 6 or 7 years final papers, and I'll put that together for you guys in a worksheet, and we can look at it, let's see if we can recognize which ones of these are proportional division theorem ones and which ones of these are similarity ones. Like I said, sometimes they have these horrible level 4 questions where you have to use both in one sum. You have to use similarity and proportional division theorem in one sum. That is a possibility. So, today's discussion is about locating the triangles that must be proven similar. Okay, we have to try and locate the triangles, because if you can't locate the triangles, you can't do the similarity proof, and if you can't do the similarity proof, you cannot do whatever statement they want you to find. So, in this one it says, and it is in your notes, by the way, it's example 10 on your notes. I just cut it out, and it's a worked out example in your notes. Okay, so now it says, circles ABC, so there's circle ABC, and because they call it circle ABC, you know for a fact A, B, and C are concyclic, meaning they're all located on the circumference of the circle, which means that AB, BC, and AC are chords of that circle. Do you understand? They don't have to state that. The moment they call it circle ABC, you know all of this information automatically. So that's the first circle. And then circle ABD intersect at A and B respectively. So the two circles intersect at A and B respectively. AC is a tangent to circle ABD, and AD is a tangent to circle ABC. So you've got those two tangents. Prove that. Now, whenever you get that proof statement, you grab a highlighter or a Koki or a colored pen or a colored pencil. Got it. And you start with the following. You say, I want side BC. So you highlight BC. And generally, you need at least 2 colors. Some questions you might even need more colors. So they say BC over AC. Now, if AC joins up with BC, so if they're connected, if they're linked with a common vertex, you can keep the color the same. But the moment they're not connected with a common vertex, change the color. Do you understand? So you go BC over AC, and then you should notice we can close up a triangle. Once you get the first 2 sides, you can close up the triangle, so we can close it up with AB. Then we go to the rest, and they say AB. So you have to highlight AB in a different color, there, over AD, so there's AD, So how do we close up that triangle? We close it up with BD. So the moment we've closed it up, we can at least start our similarity proof, because now we have an idea of which two triangles we need to prove similar in order to get that statement. Got it. Now when I start this, I'll say in triangle, and I pick one of the two. Really doesn't matter. I'm going to pick the green one. And I normally list the vertices in alphabetical order. You don't have to list it in alphabetical order. You can list it in any order you want. I'm just going to go and say it's triangle ABC. And then you'll see I go and I stop. I leave it blank. Why do I leave it blank? I need to first see what are the angles that correspond. If I write the first one, ABC, and the second one, for instance, ABB, I might have written the angles not in corresponding order, meaning the equal angles are not in the same order, which means when I get to that proportionality statement, that's also going to be wrong. So that's why I just leave it for now. I'll fix it just now. So I'll start by saying, number one, I always like to look at the tangents first. Quite like the tangents. So looking at the tangents, do you guys agree? A2 is going to be equal to C. I'm going to write it in the order angle C is equal to angle A2, and that's another habit that I have. I named the first triangle triangle ABC. So all of the angles of triangle ABC, angle A, angle B, angle C, I'll put on the left-hand side. And all of the angles of the other triangle, I will put on the right-hand side, because that actually makes it easier in the end to spot the corresponding angles. If I start messing around, like I'll start with the first triangle there, so I'll have angle A from the first triangle equal to whatever angle from the second triangle, and in the next one, I start with an angle from the second triangle first. That confuses things. Then I can't see the corresponding angles. Do you understand? Okay. So I'll say angle C is equal to angle A2, tan chord. And then I can also use tan chord over here, where I can say that angle C1, A2, wow. You'd swear I wrote accounting just now. Okay, angle A1 is equal to angle D. That's also tan chord. Which means the last set of angles, and this is why it's such an advantage to write the first triangle, all the angles like this, because now I see it's triangle CA, what's missing? Angle B is missing. So that's going to be B1. And there I've got angle AD, so I've got angle A, angle D, so I'm missing angle B2. And that's going to be sum of angles of a triangle. And then I can make the statement, therefore, triangle ABC. And because I was so careful with the way I wrote it, I can read A, B, C is similar to D, B, A. Can you see that? So I can see A, B, C, D, B, A, because I've got them, all of the angles of the one triangle on the left-hand side, all of the angles of the other triangle on the right-hand side. So the moment I know the order here, A, B, C, I know the order there, D, B, A. And then I can just complete it over here as well. And my reason, angle, 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 or equiangular triangles, up to you to decide. And then I can go back to what I was actually trying to prove. And because I've made sure that the triangles are written in the correct notation, so in the correct order, I can then just go and say BC over there, AC over here, AB over here, AD over there. Perfect. So I can literally just write it down. I can literally just go and say BC over AC. So look, BC over AC is equal to AB over AD. And that's going to be from similarity or similar triangles, and I'm done. Got it? Not easy. It's not easy, especially if you're doing it the first couple of times. Because trying to find those two triangles can get very tricky, and it is, unfortunately, there's a lovely word, pedantic. You know the word pedantic? Okay, some of you guys are naturally very pedantic. I'm super pedantic. Okay, I'm so pedantic, I'm probably bordering on OCD. Okay, some of you guys, you're not that pedantic, but the more order you create in your proofs, the easier they become. The more messy they are, the more all over the show they are, the harder they become. Okay, so we look at the next question. B then says prove that AB squared is equal to BC times BD. Now, before you try and find two brand new triangles, just careful before you try to do that. First, go and look what you've already done. And when I say look at what you've already done, if you look at AB, AB is over here. If you look at AB again, because that's what AB squared means, it means you're going to use AB in the one triangle and you're going to use AB in the other triangle. So you've got AB over here, but you also have AB over there. Can you spot that? Then BC over here, there that is, and then BD, there's that one. So do we really need two brand new triangles? No, it's already in there. All of the sides I need are already there. So you can start by saying AB over DB. Yes, sure. Okay, and by the way, DB, BD really doesn't matter. Is going to be equal to, so I've got AB over DB or BD, is equal to BC over AB. And I can again just go and say similar triangles. And then we just do the cross multiplication. We just cross multiply. So we go AB times AB is AB squared, and that's going to be equal to BC times BD, and I'm done. So don't go and reinvent the wheel. Don't go and find two brand new triangles when it is very, very possible that you can just use the same two triangles again. Normally, let the mark allocation give you an idea whether you need to do a similarity proof again or whether you can just use the previous one. If the second one, for instance, counts about 2 marks, there's no way you're going to have to do a similarity proof all over again for only 2 marks. You can just use what you've already proven. Do you understand? Okay, so let's try another one. So this is example 11, and it says, PQ and PS are tangents to the circle, so we have the two tangents again, and these two tangents are from the same point. So what do we know about tangents from the same point? Equal length, which means it's an isosceles triangle. Okay, and we've also spoken about the fact that if we had radii coming out from there, it would have been a kite, and it would have been a cyclic quadrilateral because of those 90 degrees opposite each other. So we've got lots of stuff there, but currently we only have the fact that it's an isosceles triangle. Then it says ST, RS, and RQ are chords, and QS is joint. So that's not too important. But they do tell me that PQ is parallel to ST, which they have indicated on the diagram. Okay. So the question says, prove that QR squared is equal to RS times RP. So we again grab our highlighter. We say QR is listed twice because it's squared. So you have to highlight QR in one color and then immediately in another color. So the moment there's something squared, you highlight the same one twice but in 2 different colors because we need it in both of the 2 triangles. Got it? Then they go and they say RS. So RS goes over here, and I think it's going to be easier just to put this in pink, and then I can complete the triangle. Where will the triangle be that I complete? QRS. There. Then we need RP, so I'm going to highlight RP over there. So where will I complete this triangle? PQR. There you go. So now that we've identified the two triangles, I'm going to give you guys the opportunity to now do the triangle proof and see if you can get that whole thing, that order going. Keep all the angles from one triangle on one side, keep all the angles from the other triangle on the other side, and then make sure that they're in that corresponding, not necessarily in the order you wrote at the first statement, okay, but just make sure they stay in corresponding order. So try it, please. So let's take a look. So if you started those two triangles, again, we have got our tan chord theorem. Did you spot the tan chord theorem? Yes? Q1 is going to be equal to S2, tan chord. Then number 2, trying to see maybe the parallel lines are going to help. Yes, the parallel lines will actually help very well. Q2, or I don't want to start with Q2. Okay, this is now where it becomes a problem. If I start with Q2, I'm jumping into the pink triangle, do you understand? But at the end, you'll see just now at the very end, I'll make sure it's in the correct order. So if I mess around a little bit, because I just had to start over there, you'll see when I make my deduction, I'm going to make sure it's in the correct order. So I'll start at Q2, even though it's not part of this triangle, I know. So Q2 is equal to angle T. Why is Q2 equal to angle T? Yes, Oliver. They're both subtended by chord RS. So RS subtends Q2 on the circumference, but RS also subtends T on the circumference. So it's angles in the same segment. Then, we can then jump from there saying, but angle T is equal to P1. Why is angle T equal to P1? Alternate angles. Sorry, Oliver, otherwise I'm going to ask you the whole time. Okay, so alternate angles because of the parallel lines. And don't forget to mention the parallel lines. So that's going to be PQ parallel to ST. And then I can finally go, and this is the part I'm going to put in the correct order. So I've now proven that P1 in the green one, which I keep on the left-hand side, is equal to Q2 in the pink one. So I'll just rewrite it now so that's in the correct order. P1 is equal to Q1. So I keep that order, the left-hand side, right-hand side order. Okay. Then luckily, the third one's the easiest one of the lot. I've got P, I've got Q, so what's missing? R. You guys agree? Yes. Thank you. Q1 is equal to Q2. Oh my goodness gracious, this is so much fun. No, it's P1 equal to Q1. Q2. That's it. Thank you. Do you know how much nicer it is now that you guys are here to correct my mistakes? Because it's super difficult when I was recording all of those videos to imagine somebody as I'm writing going, ma'am, you made a mistake. That was very difficult, I have to say to you guys. Okay, so we've got P1 equal to Q1. So you've got PQ, the last one is going to be R. So I know that R1 in the green triangle. And then over here, we've got S, we've got Q, so we also need R. So this is going to be that angle R, which I'm just going to call angle QRS. Now, by the way, you can call it angle QRS, or you can call it angle R2 plus R3. It's up to you. And those are going to be equal because of sum of angles per triangle. So therefore, triangle PQR is similar to triangle QSR. So again, look at the way I do it. PQR, QSR. And I can write it over here in the correct order as well. And this is going to be because of angle, angle, angle. And then I go back to what I originally wanted. I wanted QR twice. So I'm going to put it over here, and I'm going to put it over there. I needed SR, or RS, so there, and I needed RP, so there. So that's actually pretty easy. I can say QR there over RS is then equal to PR, or RP, over QR, and that's going to be similar triangles. And then if I multiply across, I get that QR squared is then equal to RS times RP, and I'm done.